Hey everyone, it's Matthew Bolin here with my second video on seed finding and reverse engineering. I just moved into my new apartment, so I finally have time to record this. I know it's been a while. But yeah, so before we get into things, I wanted to say that, again, this series is about covering the theory and the mathematics behind some of the stuff that I've been doing in seed finding. If you want to go out yourself and write a seed finder, my friend Neil has recently been putting out a really wonderful series on sort of the day-to-day seed finding projects, like how to actually, if you just want to find something very simple, he's kind of been making a series on how to do stuff like that and how to use the libraries that we've developed over these past 2 years. But yeah, so I'll link that in the description. But today, we're going to be reviewing what I consider to be my most important contribution to seed finding as a body of knowledge. And that is a way to model a lot of seed finding problems as problems in what's called integer linear programming. And if you don't know what that is, it's okay. I figured this stuff out on my own without knowing what that was. It's only now, with sort of having more math underneath my belt, that I understand that perspective. But I do believe that this could be understood by someone who wants to understand it. You have to want it. Who's not been exposed to much of this stuff before. That being said, my first video in this series is absolutely a prerequisite to this video. I'm going to be using the formulas that we derived there pretty freely, and I'm not going to hold your hand so much when we go through modular arithmetic. It's just because I'm not going to finish this lecture any other way. The second thing is that I am going to be using a little bit of linear algebra in this video. If you've not seen matrices before, if you've not seen linear algebra before, they're not used in such a crucial way. They're mostly used to state the most general case of this problem in a nice notational way. So it's not critical that you've seen them before, but I think your understanding and appreciation of this video will be vastly improved if you have a little bit of linear algebra under your belt. And to that extent, I would highly recommend watching at least the first 3 videos of 3 Blue 1 Brown's Essence of Linear Algebra series. That's all you really need to understand this video, and I think that even an understanding of linear algebra at the level that those videos will give you will unlock a lot of doors for anyone who's comfortable with that material. You'd be surprised. Linear algebra is one of the most important mathematical subjects, and it doesn't get taught until college for a lot of people, although it's definitely not college level math, at least not the amount that we need today. And I do hope that if you are a person who is sitting here and worrying that you don't have the prerequisite knowledge to necessarily follow along with everything I say today, I hope that the fact that this stuff applies to Minecraft and unlocks a lot of cool new seed finding techniques for us, I really hope that that can be sort of inspiration to learn stuff like linear algebra and, to a lesser extent, lattices and linear programming. Because this stuff really is so useful, so cool. And I think I think everyone could gain a little something by knowing it. Now, with that out of the way, I'm going to be taking a lot of drinks of that water today. With that out of the way, let's get into the presentation. Okay, so just to recap from the first video, because I know it's not fresh in everyone's mind, a LCG, which stands for linear congruential generator, not going to say that again, is a pseudo-random number generator. And again, it works in a very simple way. So it has an internal number called the seed. And every time you want a pseudo-random number from the linear congruential generator. The LCG updates the seed by multiplying it by some number A, adding some number B, and taking the remainder when divided by M. So I have that written out there. Seed is assigned. I hope you can see my mouse, otherwise this will be a little awkward. Seed is assigned A times seed plus B, and then this whole thing is taken modulo M. And again, that means the remainder after dividing by M. Watch my first video if you want to see more stuff about LCGs in depth and the derivation of the formulas that are going to be on the next slide. In particular, almost all randomization in Minecraft generation, with the exception of biomes, is done using a linear congruential generator, well, an LCG, which has this A number up here equal to this, and it has this B number equal to 11, and it has the modulus being 2 to the 48. So we're going to be dealing only with that specific case in this video in order to keep ourselves grounded in sort of Minecraft, because Minecraft's a very tangible thing and it's nice to get a hold of. But of course this theory applies for the most part, it applies for any LCGs. You can maybe choose some pathological constraints, like some guy in my last video commented something about A being 1 or A being 0, which might break a little of this stuff. But for all reasonable LCGs that are in practice, this video will apply. And the final thing that we established in the last video, or at least mentioned in the last video, is that this is a pseudo-random number generator, but if you just took the seeds as your pseudo-random numbers, that's kind of not very useful, because these seeds are massive numbers. They're between 0 and 2 to the 48, so they can be as large as 280 trillion. And most of the times you don't want random numbers that big. You want random numbers between 0 and 1. You want random numbers between 1 and 5, whatever. And so the Java programming language has a number of methods that you can call to get a random number in the range you want and of the data type you want. And the important fact about Java random that we need to use is that if you have two seeds that are close as seeds, so just as their raw seed value, they're sort of close-ish in values, when you call one of these methods, which turns that seed into the type of number you actually want, if the two original seeds were closest together, the two results will be closest together. And that's an important general fact. It's not too possible to make that so rigorous, but to apply this stuff, you really do need something like that to be true. Because most of the time we can't work at the seed level. We have to work with the actual math Minecraft does with these seeds to produce things. In the last video, we established that if we have a linear congruential generator, we have another linear congruential generator which reverses the first linear congruential generator. So what do I mean by that? Well, if you have an LCG and you have a seed 0, and then you put it through the LCG and you get a new seed, seed 1, there is another LCG which can take seed 1 and it pushes out seed 0. And so that's a fact we established in the last video. This is going to be important for us because near the end of everything, we're going to be reversing a bunch of LCG calls. And also important is that we have an efficient formula for calling an LCG n times. So this one's a little bit scarier. Again, we established this in the last video, so please go watch that if this is feeling lost, or just accept my word that if you have an LCG and you start out with a seed 0 and you call it n times to get to seed n, there's an LCG out there which you could have called just once that would send seed 0 to seed n, for any choice of seed 0. And yeah, and in particular, because LCGs are very fast to calculate, this formula gives us an efficient way to jump forward or even backwards n calls. And if you care, there's some complexity information at the bottom of the slide. So, with that out of the way, we are going to consider a very general problem in seed finding. Okay, so, and that is to find Java random seeds which will give desirable features in game. And so, what do I mean by giving desirable features, right? The most common way that Minecraft code uses to determine if something should be there or not is it calls some method of Java random, and it tests whether it's between two numbers. There's many examples of this. I'll get to some in the next slide, I think. And not only, and so if we have a test like that between a is less than or equal to next something here just means some method of Java random's output is less than b. If that's satisfied, presumably what we want will happen. And because of what I said earlier about it's close seeds mapping to close outputs, if we have an inequality that a is less than or equal to the output is less than b, we can find some a bar and b bar such that a bar is less than or equal to the actual seed that call used to generate its number is less than or equal to b bar, excuse me. And that's mostly true. We can find those those a bar and b bar for basically any method in Java random. The major exception is next int when you call it with an argument that is not a power of 2. That one ends up being really annoying to deal with. We can handle it in the general theory, but I'm going to need to establish the entire method first, and so I've hidden the explanation for that in the appendix. It's not so important, but yeah, you need some extra tricks for dealing with that one. But for the most part, this leads us to this problem. Because we don't just want one thing most of the time in seed finding. If you only want one thing, that's a very easy problem. That's something we've known how to solve for 5 years now. And what's hard is if we want a bunch of things to all go our way on one Java random object. Okay, so we're going to write down this problem in a general way. So just let seed sub alpha be the alpha. Why did I name it alpha? Anyway, the alpha seed in a Java random sequence. And in this, we're going to take the convention that seed sub 0 is the seed that we initially had Java random set itself to. And so to solve our general problem of finding a bunch of features that all went right, we need to find all possible values we can set that initial seed 0, such that some a sub 0 is less than or equal to the seed at index alpha 0 is less than or equal to b 0. That's where a and 0 and b, where a sub 0 and b sub 0 are whatever bounds we have for that feature to be present. And we go on like that with n inequalities for the n features that we want to occur. And it's going to be really, really convenient for us, if you recall our formula to jump forward and back n calls. it's going to be very, very convenient for the purpose of this presentation if you allow me to assume that alpha sub 0 is always 0. That is to say, the very first set of inequalities that we care about satisfying, we care about on the very first seed in our sequence. And if that's ever not the case, you can just re-index so that it is the case, and then at the very end of the whole process, reverse yourself back to wherever your actual first seed was. So that's never much of an issue. So we're going to be taking that as convention because it really will make some of the math easier. So that was a lot of abstract stuff, a lot of, let me get the mouse out of it. A lot of abstract stuff, a lot of numbers, a lot of algebra. Let's look at an example in a game. This one's my favorite. This is the problem I was considering when I first came up with this sort of algorithm to deal with this problem. And this is a 12-eyed portal. So 12 eyes, as you might guess, need 12 features to go right. And those features are these eyes around the portal frame. So the way that these eyes work is that they have a 1 in 10 chance to have an eye here already. And if all 12 of them are filled, the end portal will light. And that's something that we really want to happen for, say, speedrunning seeds. So the way that these actually do the 1 in 10 chance is they generate a number between 0 and 1, and they check if it's bigger than 0.9. So here's what that looks like, sort of more algebraically. So yeah, here we go. We are actually calling the next float method of Java random. It's not too important to understand exactly what that entails. But next float is greater than 0.9 if and only if the seed at the index we care about is between this awful number. This number is roughly 9/10 times 2 to the 48, if you're wondering where that comes from. Roughly, there's, again, some weirdness. And it's also between, we can't have 2 to the 48 as a seed, but yeah, but this is basically just a condition that the seed is valid, that it's less than or equal to 2 to the 48 minus 1. And so if these 12 inequalities hold, then we will have these 12 eyes all filled. And here, this is a case of where the alpha sub 0 index from 2 slides ago, this thing, it's not 0 in actuality. It's at 761 because, again, we have 761 stone brick calls or whatever going on. But we're going to re-index so that that's 0. So let's, I think that's true on the next slide. And 12 eyes are not the only problem. So here's a list of problems where I've applied this. So if you've watched my video on dungeon-based seed cracking, we currently have that implemented into a mod, into a program called Seed Candy, a number of other things. Dungeon-based seed cracking is now possible in a few seconds using the algorithm that I'm going to be developing in this video. And it can be formulated exactly as one of these problems. There is tree-based seed cracking, which, yeah, that was a little bit relevant for pack.png. It didn't end up being used in the final iteration of the pack.png finder, but I think had we not gotten access to the Minecraft at Home project, it would have still been the only way to go. If you've seen on my channel, I recently uploaded a live stream of us obtaining Bedrock in 1.8. That was a case where I used the algorithm I will be developing in this video to crack the random number generator, which does a lot of like spawning and stuff in the end, which we needed to manipulate to obtain Bedrock in that speedrun. I have on my GitHub a program which can crack the internal randomness of droppers. So if you want to cheat at Redstone minigames, you can. And again, we can formulate it as one of these problems. And again, I have the program which can do it. For seed finding, again, you can find chests with rare loot combinations. These are exactly this sort of problem. So I think I found a chest with I found a desert temple with pretty much the max number of notch apples in it somewhere. Weird trees. That's a little bit hard to explain, but I might eventually put out a video on some of the weird trees, caves, and weather seeds, because I kind of have a big bucket of seeds that I think are a little cool, but they take 2 seconds to explain, and they're a little bit esoteric. And this stuff is also at the heart of my favorite Minecraft project I've ever done. And I swear I'm going to publish a video on that soon. It's just, I have to explain the math first, because I will die inside if I don't. And there's a few more things, too, that we've used this for. Don't believe that this is a comprehensive list at all. And like in particular, if you want to reverse a random object from a next double or a next long, this can do that. And also, this is not the only linear congruential generator in existence. Minecraft is not the only video game in existence. Again, this theory applies to general linear congruential generators. I had an interaction with the Pikmin 2 community, and I showed them this sort of method. Although I don't know if it was all that useful to them, but they did have one of these problems, and I was able to solve it. Right, and so to that end, we have implemented the algorithm I will be going over today in a project called LATICG. I'm sure I'll link the GitHub in the description. And currently, LATICG is able to beat brute force on a GPU, and LATICG works on a CPU. So I prefer that, but I just hate GPU programming. And it beats brute force when it deals with around less than 24 constraints. So if you want 24 things to go right on a random object, that's a good threshold for anything less than that. That's a good threshold for LATICG is probably right for you. And the other thing is that the quality of the constraints matters a lot for this algorithm. So if you have a bunch of constraints that give less than 2 bits of information, that's going to impact the runtime. We'll hopefully see why that should be the case later on in this video. And I'll also say that LATICG is not done. Currently, we are only handling Java's LCG. There's often cases where you want to solve maybe hundreds of thousands of similar problems at once. And for that, you would really love to cache a lot of important information, and we currently don't have support for that. And we're also not able to recognize when the user has maybe given us constraints that will only make the algorithm less efficient. So we've not implemented that, but I will be uploading a tutorial once the API is more presentable. Well, I guess the API is a bit better since I wrote this slide, but I will be uploading a tutorial on how to use LATICG, and that way, if you're just a programmer, you don't want to understand the math behind all this. You don't want to code all this stuff from scratch, because man, I don't blame you. We've got you covered. You can import the library or whatever, and you can use this algorithm. Okay. Back to 12 eyes, right? So we've re-indexed, first of all. So we're looking at seed 0. Again, this is really seed 761, but it is far more convenient if we view it as seed 0 and then just reverse 760 or whatever it calls when the time comes. And again, we want these 12 constraints to be satisfied to get a 12 eye. So we need 12 consecutive seeds all of which satisfy these bounds. Okay? And now we're going to use the fact that these numbers that we want to satisfy these bounds are consecutive seeds of an LCG. And we already have a formula for seed n in terms of our seed 0, right? So that goes back to what we established in the last video. We have a to the 0. Well, okay. So if we want seed n, we take a to the n times seed 0 plus b times a to the n minus 1 over a minus 1, all mod m. And I've written min 0 and max 0 here just because we're going to be dealing with this in a general form later, and these numbers are huge. There's nothing too important about their actual numerical values. So we now have all of these inequalities in terms of seed 0 alone, but there's something a little awkward here, which is this mod m. So mod m doesn't really play too nice with inequalities. In fact, it's a little bit illegal to write equations like I've done here with like a mod m in between. Inequalities, pardon, not equations. And that's kind of because, well, let's say for an example, 6 and negative 2 are equivalent mod 8, but 6 is between 5 and 7, but negative 2 is certainly not between 5 and 7. So you have to be a little bit careful when defining what you mean by this. So currently I just mean mod m being like the least positive residue. But that's not too important because we're going to delete those. We're going to get rid of those. So we're going to... So how do we get rid of the mod m? Right. So the first thing we're going to do is mod... Let's see. If you have a number and you have a number mod m, so again, 6 and negative 2 mod 8 as my quick example, their difference will always be a multiple of m. So in the case of 6 and negative 2, 6 minus negative 2 is 8. 8 is a multiple of 8, and that holds in general. Because all you're doing when you're taking a remainder is you're subtracting off the biggest possible multiple that could fit into your number. So we can really think of this as meaning we have this number here, which could potentially be awful, and we can add some multiple of m to it, which makes it fall between these bounds. I hope that made sense. In general, if I say anything that doesn't make sense to you have questions about, please just ask in the comments. I'm sure, you know, those of you who are motivated enough to have made it this far, you'll get it. And so I also, just for sanity's sake, I subtracted the addend off of each side. And yeah, the new thing to recognize is that we've introduced a new constant, k0. So we don't know what this is. This is another sort of variable, like seed 0 is a variable. While everything on the left-hand side is fixed, everything on the right-hand side is fixed, and m is fixed, a0 is fixed. And so this is now a system of 12 linear inequalities in 13 variables. And in fact, you might notice that a0 is 1. A to the 0th power is 1. This is kind of why we wanted to reindex so that we would get a 0 here. So that this becomes 1. And over here, this a to the 0 is 1 minus 1, 0. So this whole minus b thing cancels out. And this whole minus b thing cancels out. And we can, as long as we presume that seed 0 is between 0 and 2 to the 48, well, you know, between min 0 and max 0, I guess, in my notation here, As long as we presume that, we can effectively ignore the existence of k0 at all, because we know that k0 will always be 0 in that case. So with that in mind, here's what everything looks like when we plug in. Perhaps a little less scary, perhaps a little more scary. Depends if you're more scared by numbers or by algebra. And yeah. So, oh, whoops. I forgot to re-index in my notes up here. This should be k sub 1 through k sub 11, not k sub 12. We don't have a k sub 12. But okay. And yeah, so as long as we presume seed 0 should be between 0 and 2 to the 48, it's fine. We know that the invisible k0 that should have been here is 0. And so 12i's becomes, can you find 12 integers, 1 seed 0 and 11 of these k's, which satisfy all of these inequalities? Whew. So I hope you could follow all that algebra, because we're going to quickly do it in general. This is where the matrices show up. You know, please don't be too scared. It's mostly for notational cleanliness. But again, you know, if you've not seen a video on linear algebra, if you don't know how matrices multiply, there's not much I can do. Do consider watching that Essence of Linear Algebra series, because I do think it's fantastic, and I think you will learn a lot if you do so. So yeah, so we're going to make all these definitions to kind of hide the complexity. So we're going to have A is equal to this big matrix, B is equal to this big vector, min hat is, oh, I guess this is B hat. Min hat is equal to this, to the vector of all the minimums. Max hat is equal to the vector of all the maximums. And the question is, why would we think of writing matrices here, right? Because, well, most of you will have encountered matrices in the case of systems of linear equations. So you'll have, technical difficulties. Okay, you'll have a bunch of equations which look like this, but instead of the inequalities, you'll just have that all of these are equal to something, and you have to solve for all the variables over here. And inequalities really aren't so different. What we have here is we have quite literally a system of 12 linear things in 12 variables. And so that can be captured with a matrix. So if you look, 1, there's a coefficient of 1 on this seed 0. That corresponds with a coefficient of 1 down here in A. There's a coefficient of A to the alpha 1 here. Well, I mean, here, I guess. All right, because we're working in general here, so we still have to use this alpha notation. But there's that coefficient on C. And now on K1, which is our next variable, we have a coefficient of M, or 2 to the 48, and that corresponds there. And then we have a coefficient of M on K2 and this row, and we go all the way down to A to the alpha n minus 1 is the coefficient on our very last equation, and we have a coefficient of 2 to the 48, or M, on our very last variable of the K's. So that's all that this matrix wraps up. Is it wraps up a system. It basically just encapsulates the information of the coefficients of our system of linear equations. Inequalities, pardon. And likewise, B is just this this constant thing we're subtracting from both sides in vector form. And same thing with min 0, min 1, min 11. You know, I already indexed them like they were vectors because I knew this was coming. And so, if you're willing to accept big scary matrices, big scary vectors, we can write this problem in a very nice way, which is some minimum vector is less than or equal to a matrix A times some integer vector plus B hat is less than or equal to some max vector. So, if we can find integer vectors such that this is satisfied, I claim that that is exactly equivalent to seed finding. Okay, so let's see why, right? Oh yeah, subject to this condition as well, that we have the bound on seed 0. And the reason why is actually pretty simple, because if we actually trace through, you know, what x hat times a is, we're going to see that a times x hat plus b hat, it's just exactly what we had in the middle right here, all of these things. So if you treat all of this entire middle column as a vector, this entire middle column we have now written as a times x hat plus b hat in this notation down here. And these are just seeds. So if we can find an integer vector x hat such that this is satisfied, we have then a list of n consecutive seeds. Well, not even consecutive. We have a list of what the seeds are at all the indices that we're targeting, and we know for fact that they work and that they're valid. And so by just substituting in the equation that we derived last video, in terms of seed 0, to get all of these inequalities basically in terms of this one variable, and then accounting for the modulus crap, we now have a very different formulation of the problem. And it turns out that this formulation of the problem is going to reveal to us a massive weakness of linear congruential generators. And for this, we're going to take a step back, because I know that this is going to be very overwhelming, and we're going to look at some pretty pictures. So we're going to understand. Before I get to the pretty pictures, sorry, if we're going to understand this sort of inequality, we need to understand basically what happens when you multiply the set of all integer vectors by a matrix. Okay, that is ultimately the structure that we're going to be trying to understand this video, and we're going to be targeting this video, because this right here, the fact that you can write a tuple of seeds at indices you know in this form, this is the weakness of LCGs. But to see why that should be a weakness, we're going to go over and we're going to graph some of it. So because all those big numbers that we use in practice are a little terrifying, we're going to consider a much smaller and simpler LCG, which is seed is assigned 5 times seed plus 2 modulo 8. Okay, and we're going to see this weakness that I have demonstrated so far. We're going to see it visually, and hopefully the visualization will help you understand what I'm on about. So let's start out by just saying seed sub 0 is 0, okay? So we have our machine here for getting the next seed. We take 0, we pop it in for seed. 5 times 0 is 0. Glad I still know how to do that one. Plus 2 is 2. And then 2 leaves a remainder of 2 when divided by 8. So our new seed is 2. Okay? And we're going to represent this fact that seed 0 gets sent to seed 1 like you would represent a function in your, high school math class, right? So seed 0, we're going to put on the x-axis. So from now on, I want you to think of the x-axis as the axis of the first seed, the seed 0 axis, if you want. And the y-axis will represent the seed 1 axis. Okay, so here we can see the point at seed 0 equals 1. our LCG spits out 2. And I've not bothered labeling the axis, but 0, 2, I think you get it. And we can do this for all the seeds we have in the LCG, right? So we can extend this process. So say take seed 0 equals 1 right here. So 5 times 1 plus 2 is 7, modulo 8, still 7. And so that would send seed 0 to 1. Seed 0 is 1, and then seed 1 is 7. So we get the point 1, 7 up here. And a similar process generates all 8 of these points. And I claim that this image already hints at the massive disaster of LCGs. Oh, by the way, I wanted to mention this. I messed up. I did this whole example with this LCG, but this LCG that I'm using as my example has a slight problem, which is that you really don't want this plus 2 to be a divisor of 8. You don't want the thing you add to divide your modulus. So if you actually try this LCG, if you try and use it to generate random numbers, the random numbers will be much lower quality than you would had I put a plus 3 right here. But it's so small, and it still gets the point across, it still gets this image across. But yeah, if you're writing your own LCG, do make sure that this is co-prime to this. Okay. So this image already, if you think about it, imagine for a second that LCGs were truly random. We would not expect this image, right? Because we don't expect the second seed to depend at all on the first seed. But here, there's very clearly some kind of pattern going on. I think I highlight this in the next slide. Yeah, look at all these lines that these points seem to be falling on, right? Isn't that a little weird? If LCGs were truly random, we would not expect to see any sort of pattern here at all when we're plotting the first seed against the second seed. But yet here we have these lines which are evenly spaced, and they clearly intersect at like regular spots. And yeah, this is the flaw of LCGs. And the flaw is that the seeds are linearly dependent. So what I mean by that is that if you have an original seed and then its next seed, and then you nudge the original seed by some tiny amount, and then look at that nudge seed's next seed, the resulting 2 seeds of both your original and your nudge seed, they will be nudged by a predictable amount, which is only a function of the original nudge. And that is why we get these patterns, okay? And we can also see why this pattern should arise if we look in our earlier algebra in the matrix form. So here's our earlier notation. Again, don't be too put off by this. So we have A is this huge matrix, B hat is this huge vector, and we have an example which, it just shows you how general this formulation is. So we're going to plug in. We're dealing with 2 calls, so we kind of have a 2-dimensional structure here because we're only graphing 2 axes. We absolutely can work in higher dimensions, and that will be important to us later. So we can plug in our n is 2. Our first seed was seed 0, so our alpha 1 is these should be alpha 0 and alpha 1. Excuse me, I re-indexed to 0 index things. This should read alpha 0 and this should read alpha 1. Every time I say alpha 0, I think of the Go engine. But okay. So besides that indexing error, our LCG here, we chose our multiplier A as 5, our addend B is 2, and our modulus M is 8. And so if we plug in M is 8, N is 2, we get A is this matrix, which is much smaller and more approachable than this massive general form sort of thing. And B hat is this thing, which also looks very approachable, right? And if you remember, we had that the set of all seeds, so in this case, the set of all pairs of two consecutive seeds, is describable as A times X hat plus B hat, right? And if we expand this out, if we do matrix multiplication, so x0 here is the first component of x hat, we have x hat times the first column of A, 1, 5, plus x1 times the second column of A, 0, 8, plus 0, 2. For all the integers, x0 and x1, we have that this is the pair of all consecutive seeds, well, seeds up to a multiple of the modulus. So let's see that in action. So here's the picture that we get, okay? So we just took this equation, okay? And behind the scenes, all that the code I used to generate this image is it's just going through all the values of, well, a reasonable number of values for x0 and a reasonable number of values for x1. And it's computing the vector corresponding to this equation. And we get this lovely image. So we can see our earlier pattern, which we got by just naively plotting the seeds right here. That is present in this new set as the green dots. And all the extra dots that we get on the outside are seeds which are valid, but which are still valid, but modulo n. So for example, this 0, 2, this is a valid pair of seeds. So 0, indeed, its next seed is 2. And up here, this coordinate is 0, 10. And of course, the seed after 0 isn't 10, but 10 modulo 8, which is our modulus here for this LCG, is still 2. So that's we kind of tiled the plane with this green set. Because, yeah. And these extra points, they're sort of an artifact, but they're a little bit helpful for my intuition, so I'm going to leave them there. And it's also important for us to address our equation right here. So we have x0 times this vector plus x1 times this vector plus our little b hat vector, this 0, 2. And so this is what those vectors look like on this image. So we have b hat, which is 0, 2. So that's sort of the amount we translate up this structure. And we have a0 and a1, which are the vectors who, when we look at the set of, some integer times a0 plus some integer times a1, letting those range over all possible integers, we can generate every point in this picture. So that's wonderful, right? Because by doing the algebra that seemed natural, we got ourselves a lovely description of this structure. We have discovered a structure which makes LCGs weaker than true random number generators, and we have an efficient description for it. So now our goal should be to understand the inequalities that we want to satisfy in terms of this picture, and in terms of this description of this picture, in terms of these vectors, So we have these vectors, which in essence generate this picture. And so all we need to do is add our inequalities onto this picture, and hopefully this description will be efficient enough to yield a good algorithm. So let's say we want seed 0. So again, what we used to call the x-axis, this is now the seed 0 axis. If we want seed 0 to be between min 0 and max 0, well, that's like requiring, well, okay, I still wrote x up here, but that's requiring seed 0 fall somewhere between two lines. So we have some minimum value for seed 0 and some maximum value for seed 0. And so if we want, so that yields this sort of gray region. Because if seed 0 is less than this, there's no way that seed 0 will fall, will fall between min and max. And if seed 1 is greater than this, well, then yeah, again, there's no way it's falling in this gray area. And a similar thing holds if we have an inequality on the seed 1 in this case. So that would yield, because now the y-axis is the seed 1, and we would get, if we have a max 1, a min 1 and a max 1, we would get a similar sort of bend. And the region in which both of these inequalities is satisfied, in this case, is this square. And all of the points of this structure which fall inside this square correspond exactly with tuples of seeds at the appropriate indices to satisfy the inequalities we wanted. So that means that our earlier problem, all that algebra, all that just yucky math we had to do to get here, can be interpreted entirely geometrically, which is find some integer sums of vectors which fall inside some box. And yeah, so we have a geometric interpretation of the problem, and I'm going to take a short break. I might split the video here and upload this in 2 parts, or I might be back in a moment. Who knows?